Hi, I'm Tixing Koh. I'm from Nanyang Technological University in Singapore. My talk is titled Two-qubit sweet spots for capacitively coupled exchange-only spin qubits. This work was published in July this year in MPJ Quantum Information with my co-authors Menke Feng and Lintu Zhou. They did most of the work that I'm going to talk about in the next few slides. In this talk, we focus on the exchange-only qubit, where single-qubit gates are based on the exchange coupling, hence its namesake. Two-qubit gates may be based on exchange or capacitive coupling. There are several advantages to thinking of using capacitive over exchange coupling. Namely, exchange is fast but short-ranged and has the potential for leakage. Capacitive coupling is longer-ranged, is experimentally less stringent, and doesn't have the issue of leakage. Given a clean magnetic environment in silicon, charge noise, which is typically pink or 1/f, can dominate. We believe that it arises from charge fluctuations in the semiconductor environment, making the study of optimal working points to mitigate such noise important. These optimal working points or sweet spots already have been studied for single qubit gates in the exchange-only qubit, and for the two-qubit gate based on the exchange coupling in the limit of negligible transverse interaction. So our study asked the question, do two-qubit sweet spots or 2QSS exist for capacitive coupling of the exchange-only qubits? The exchange-only qubit is encoded in 3 electron spins, which have 8 spin states, and the EO qubit lives in a total spin equals to half 2-level subspace. The Hubbard model fully describes single and 2-qubit interactions. It comprises tunnel coupling, detuning, and Coulomb interactions. In this cartoon on the right, we see the tunnel couplings as well as the individual dot detunings. But what is more important will be the outer detuning epsilon and middle detuning epsilon m. So all of these parameters have a subscript A because we are denoting the first 3 dots as qubit A. Because we are interested in the low energy dynamics and the EO qubit lives in a 111 charge region, we can perform a Schreiber-Wolff transformation to get an effective single qubit Hamiltonian. Now the key thing is that the qubit states after the transformation get dressed by the charge admixtures. It is the one state that gets dressed. We will denote it by 1 prime. So the charge admixtures are the doubly occupied states. They are as shown in this phase plot in detuning space, and are given by the alphas in this expression as well. So charge noise then results in fluctuations of these charge admixtures. There have been 2 important variants from the original exchange-only proposal. They are the always-on exchange-only qubit, or AON, and the resonant exchange qubit, or RX. Single qubit sweet spots, or 1QSS, are positions in detuning space that protect against dephasing from detuning noise. The AON 1QSS is a double parameter sweet spot in both the outer and middle detuning, and it sits at the center of the detuning phase plot and is independent of tunnel coupling. On the other hand, the RX requires strong hybridization with doubly occupied charge states and works in a higher region given by the dashed triangle. Its detuning sweet spot is a single parameter sweet spot, epsilon, whose position depends on tunnel coupling. For symmetric tunnel coupling, where the left and right tunneling are equal, the single qubit sweet spot for RX sits along the midway line, similar to the AON. It will shift out of the midway line if the tunnel couplings are not equal. Charge noise is modeled as fluctuations in these triple dot parameters, the two detunings, and the two tunnel couplings. Capacitive coupling between the two triple dots is also described by the Hubbard model. When the barrier between dots 3 and 4 is tuned higher or inter-triple dot distance increased, tunnel coupling between dots 3 and 4 can be turned off, turning off the exchange coupling as well. Then only the Coulomb interaction remains and is given by the following expression. So this Coulomb interaction is typically called the capacitive coupling. In the computational basis, as shown, it is a diagonal matrix comprising the 4 V terms. Now these V terms comprise 81 unique pairwise Coulomb repulsion terms computed with 3 electron wave functions that are constructed from analytical Fock-Darwin solutions to this tri-quadratic triple dot potential. Okay, the reason for using this potential is that it's analytically tractable. This is important because it allows this capacitive coupling to be written in terms of the triple dot parameters from the 3 electron wave function, and charge noise gets introduced naturally through fluctuations in the parameters. Here we show the exact gate sequence for CPHASE and CNOT gates. The non-local 2-qubit gate is performed in one time step T0. And then there are these single qubit gates before and after the non-local gate. The time step T0 is found from the Markov invariance as shown here. Now we assume noisy 2-qubit gates and ideal single qubit gates in our calculations, and a noise spectrum that is 1/f for the 8 fluctuating parameters. We calculate the average fidelity of the CNOT and CPHASE gates. So numerically, this will be the expression we use. But we also derive an analytical fidelity using the cumulant expansion. This has the assumption of Gaussian noise and allows us to compute the analytical fidelity in terms of the noise spectra. The central result we got was that 2-qubit sweet spots exist for multiple parameters. This was quite surprising as it was not a priori obvious. Now we define a 2-qubit sweet spot for the jth parameter, jth triple dot parameter, as the value of the parameter for which all the fluctuating V terms, delta Vi here, vanish. Okay, and we evaluate these in the weak noise perturbative limit and find that 2-qubit sweet spots exist for these parameters, the middle detuning, left and right tunnel couplings for both triple dots A and B. This can be seen in the lines plotted in this detuning phase diagram and in the equations of the lines given below. So here, the slanted line here is the middle detuning 2-qubit sweet spot. This is the left tunneling 2-qubit sweet spot and the right tunneling 2QSS. They are being shown here for qubit A. A similar plot arises for qubit B as well. Importantly, the middle detuning 2QSS is tunable via tunneling coupling ratios. With a symmetric tunneling ratio, this 2QSS is the slanted line here. This means that during single qubit gates, the Rx and Aon stay at these points, the dots, and during non-local gating, their detunings can be moved onto the 2QSS. However, if staying at the same detuning point is desired, one can tune tunneling ratios instead. For example, for such a tunneling ratio, the 2QSS is the midway line here. The qubits can then stay at the same detuning working points for both single and non-local gates. Recall that we mentioned for the Rx, the working point is only along the midway line for single qubit gates. if the tunnel couplings are equal. Right here, for the 2QSS, the tunnel couplings are not equal. In this case, it has to tune tunneling ratios to go between the 2Q and 1QSS. Here, these color plots are non-local gate times, which are faster near the top and slower near the bottom because of the larger electric dipole moments of these respective charge admixtures near the top and smaller near the bottom. Now, one can also work at the points where the left tunneling and detuning 2QSS coincide. However, gate times are longer near the bottom, as we can see from this line cut. This is the coinciding point. For the diagram on the right, however, this coinciding point, although it's a triple 2QSS, is impossible to work here because gate times go to infinity. Here we examine gate fidelities for the Aeon and Rx at the epsilon m 2QSS for this tunnel coupling ratio where the 2QSS is a midway line. For these calculations, both Aeon and Rx sit at their respective single qubit sweet spots. The top half is Aeon, bottom half is Rx, and we separate noise in detuning, the first and third rows, from noise in tunneling, the second and fourth rows. Now, plotting the gate infidelities, we see good agreement between the analytical formula and the numerical simulations. Vertical cuts along across epsilon m display constant infidelities here and here, which justifies the existence of the 2QSS. Now, here the comparison between the Aeon and Rx is for similar gate times, which are about 450 nanoseconds. But in general, Rx is slightly faster and therefore has slightly better fidelity by a factor of about less than 10. It can be operated at about 64 nanoseconds instead. In this slide, we plot gate infidelity at the epsilon m and left tunnel coupling double 2QSS. Despite the gate times being longer here, we can still achieve infidelities within the fault tolerance thresholds here and here for low enough noise strength. The standard deviation, the sigmas of epsilon noise, just needs to be less than 10 to the minus 5 MeV, but the SD of the standard deviation of tunneling noise needs to be about 1 order of magnitude smaller. This shows that infidelity is more sensitive to tunneling than detuning noise. Now, all of the analyses have got a subscript A. They are being shown for qubit A being the noisy qubit only. Okay, the same analysis will apply if qubit B was noisy. The reason is that the fidelities multiply very simply as shown. Another interesting thing is that as we recall from a few slides ago at these double parameter 2QSS, gate times are a lot longer, and that gives us over prediction of infidelity from the analytical formula compared to the numerics. Now, further optimization is actually possible. We found that there is a global fidelity optimum, which is way within the fault tolerance thresholds. It's shown by this point right here. And at this point, analytics give us an infidelity of 10 to the negative 10 and numerics 10 to the negative 6. But this is only if we have detuning noise. When tunneling noise starts to dominate, and that happens really quickly, this optimum disappears. The second important thing is that further optimization for the Rx is possible. So recall we mentioned that the Rx single qubit sweet spot shifts with tunneling asymmetry at the start of the presentation. And it turns out that it is possible to find a specific tunneling ratio such that the shifted Rx single qubit sweet spot coincides with its 2-qubit sweet spot, the slanted line. In such a case, there is no need to change the Rx detuning or tunneling parameters for non-local or single qubit gates. It can just sit here during the whole time. In summary, from the Hubbard model and the tri-quadratic toy model of the triple dot, we found theoretically the existence of multiple parameters 2-qubit sweet spots, the exact gate sequence for CPHASE and CNOT, that infidelity is less sensitive to detuning than tunneling noise, a rather intriguing global fidelity optimum for detuning noise only, and an important working point for the Rx where its single qubit and 2-qubit sweet spots coincide. So these are the three of us. So that's myself. This is Lintu, and this is Munke. We made a mock-up of this Zoom picture because for almost all of the project, we met over Zoom only. That's rather typical nowadays because of the pandemic. We would also like to thank the following organizations and programs for financial and computational support. Hopefully there is some experimental interest arising from this work. I'm hoping to see that these 2QSS are not just theory, but also experimentally possible. Thank you very much.